Thank you, Kevin. Now, do you move me around? Okay. There's the declaration of interest. Womanjika. That's how you say g'day in the language of the Waiai Wurrung people of the Kulin Nation, from where I speak to you today. And I pay my respects to their elders, past, present, and emerging. Imagine the last hour of the last day of a conference, the graveyard hour. Half of the attendees have left for the airport. Half of those remaining are nervously watching the clock for when their taxi arrives. And the other half have just realised that the bar is open. And so why are they sitting around here? Well, I hope you can settle back with your glass of a good South Australian Shiraz or whatever your choice is, just out of camera, and enjoy seeing some very quick glimpses of some amazing software. Now, I can say it's amazing software because it's the work of my colleagues, Bob Calin-Jageman, who's out there on the panel, and also Gordon Moore, who may be lurking out there also in the north of England. Yes, this is the team, 3 of us, that spans 3 continents. There are a few links here. I'm going to zip through quite a lot of slides, but there are lots of links, and the slides themselves are available here. And I'll put this tiny link up again towards the end. Thanks to the organisers who made this all happen. I've dipped into a few sessions and I've found them incredibly interesting and energising, and definitely worth the time. So I'm going to start off with a little bit about estimation and the new statistics.
Sorry, Geoff, can I just interrupt? Are you supposed to be sharing your screen with us?
That was a fundamental blunder, wasn't it?
No, I just wasn't sure if you were leading up to that or not. I'm sorry.
Let's try this again.
Looks good.
Yes, now, yes, of course, pardon me. So there is the link to the slides there. And there's Bob, who's lurking out there. And here is the first edition of our ITNS, our intro book. We're working hard on the second edition, and the big, enormous step forward from the first will be replacing the Excel software that I wrote. That's the uppercase version of Esky with a lowercase version of Esky, 2 components, Esky on the web and Esky in Jamovi, and they're the goodies I'll be talking about today. So I'm going to talk a little bit about estimation why before I get to the software. And why? Because basically estimation gives us greater insight. So this humble little interval here gives us a point estimate and an interval estimate. And I can put a plausibility or relative likelihood curve on it. Now, I'm perfectly happy if this interval is a classic confidence interval or a Bayesian credible interval, or whether you bootstrap it or whatever you do. My main argument is that estimation, pardon me, estimation and meta-analysis is what we need for cumulative science. And it's what we need if we're going to move to quantitative modelling, estimating parameters, and then estimating the goodness of fit between those models and our data. It's what scientists are increasingly doing, and lovely story, Bob very cleverly 2 or 3 years ago had a workshop accepted for the massive SFN, the 30,000 people gathering to discuss neurosciences. And one of the top draw people on his panel was Christophe Bernard, the editor of eNeuro. And it seemed to be a little bit of a road to Damascus for Christophe. And he started off by getting Bob's help to do an estimation analysis of one of his own papers, published it, and editorialized saying, in this journal, we strongly encourage you to use the new statistics, to use estimation. And then over the next year, he tracked, got comments from people who'd tried this. And at this blog link, you can read the story a year later, just a month or so ago. He wrote a lovely editorial saying, it all worked, people tend to love it, it's the way to go. And this is happening in journal after journal around the world. I'm involved with one with the Journal of Physiology at the moment. I hope to be blogging about that pretty soon. And here are some sources. This first article is one that Christoph invited Bob to write, and that was that accompanied that first editorial, urging people to use estimation. Another one in a real grown-up statistics journal, making the case for the new statistics. And then an older one that was commissioned by Eric Icke when he was editor-in-chief of Psychological Science, that came with the editorial that introduced all the new changes at Psychological Science that have been so important in moving open science forward. Introduction of badges, encouragement to use the new statistics, and that's still on the Psychological Science instruction for authors. So I'm going to talk briefly about p-values, briefly and selectively, I'll say. So think back. If you see a result like this, what do you think? Well, you think about what 5 means. You note, yes, okay, we've got something going on here. If you see this, you think, oh, well, that's a very wide thing, this big. You really go to university to discover that, or perhaps preferably the picture, even more in your face. But these two things, of course, are exactly equivalent. And the best way to interpret this O4 is to eyeball in your mind's eye what this interval is. O4 means it extends almost all the way down to 0. That'll be 0.05. And I can conclude that the confidence interval gives us this unwelcome news, maybe, that we have lots and lots of uncertainty, low precision, also never rely on a p-value. But alas, until for some enlightened folks over the last 5 years or so, this has been the discipline we've been in for so long. The one thing graduate students learn, not necessarily in their stats classes, is that to get their degree, to get their thesis in, they have to produce significant results. And this is not a new story. Here are some quotes from some very distinguished scholars, Paul Neal, etc., over more than half a century. And these are not just little comments about, well, it's a bit tricky to understand and some people don't like the backward logic and so on, but it impedes scientific progress. It's radically defective and so on. If you don't like these quotes, there are thousands more. And then 5 years ago, 2016, the American Statistical Association, all those sophisticated mathematicians who I think had rather looked down on the rest of us unwashed, as if we only really understood properly the statistical models we were using, we wouldn't make these elementary blunders. They eventually admitted that p-values are misleading. It's not what science should be based on, and we should think of evidence as continuous. The world is not black and white, but many shades of grey. Indeed, it used to be nuts, and we're very fortunate to be in a world now that is making serious moves on from that. Now, I'm not going to rehearse all the arguments, I'm sure you know many of them, of problems with NHST, but one of the things that strikes me is how visceral the reliance on significance is. Now, any of you out there who are 50 or less, I started teaching significance testing before you were born. I know well over the decades how deeply, deeply visceral and ingrained it is to flick through an abstract. O1, right, you know, there's something here. Another O1, oh, well, this is very encouraging. But should we trust a p-value? And one of the things that strikes me about p that's really poorly understood is just how large the sampling variability of p is. And so trying to tackle this visceral attachment, this visceral addiction to p-values with something that maybe is a tiny bit dramatic, aiming for that same sort of gut feel, let us hope. And you may well have seen the dance of the p-values has been around for quite some time. Here are 3 videos on YouTube. But now this is a great moment to introduce a do-it-yourself, reveal to yourself dance of the p-values, which is way beyond what my esky offered. So I'll introduce Gordon Moore, our colleague. Morning, Gordon, and a big shout out to you. And Gordon has done great work in building esky web. If you go to our homepage, esky menu, we've got esky in Jamovi, I'll talk about in a few minutes, and esky web, which is Gordon's work. So now let me see if I can get there. Its front page looks like that. There are links all through here. So if I go here and here, I hope you can see this is, you can open it in any browser, and esky web main menu. We've got dances, I'll come back to in a minute. Distributions, I'll talk about too.
Geoff, can I cut in for a sec?
Yeah.
We're just seeing your PowerPoint. I think you have to share your screen, not just an individual window, to get it to show the web.
You are screen sharing. Stop share. Oh, that's very strange. If I stop share and then share screen and then go there, you see that now? No, sorry, I went to the wrong place. Do I have to stop it again? When I change what I'm showing on my screen, there, are you seeing,
Yep,
seeing the cover of that book there?
Yep, we're seeing the web now.
Okay, let's see if I can do that better next time. Apologies, I've got to, right. Oh, that's a bit of a problem because I do a fair bit of this changing. So here are buttons for the various goodies here. I'm going to just look at a brief look. If we go to distributions, then I can do things like, say, two tails and areas, and I could read off tail areas, one or two tail, and critical values. If I want to work in original units, I can display an x-axis up the top, which here I've made with a mean of 100, standard deviation of 15. So I've got basically an IQ score. You can translate between X and Z or Z scores down the bottom here. For a T distribution, I can, the T is the red one, and I can show you how its shape changes and relativity to normal changes as I change the degrees of freedom. And I can do the same thing again and show you two tails and tail areas and so on. So a basic tool. Let's go back to the main menu, and I can show you a few things about Cohen's D. And we can say turn on overlap area or a number of other areas and have a bit of a feel for how much overlap there is. Even when you go down to D, can you see it up the top? It's a D of 0.5, which we think of as quite a decent size D, Cohen's D, and we've got lots and lots of overlap. Let's go down to precision for planning, one very close to my heart. In an NHST world, you use power to give you some guidance as to what sample size might be adequate for the study that you're planning. In an estimation world, the corresponding idea is precision for planning. And so I will say something like, well, I want to aim for a precision of no worse than plus or minus 0.4 units of D. So I want MOE, the margin of error, that's half the length of my confidence interval, to be no more than 0.4. What do I need? For 2 independent groups, I need 2 samples, each of size 50. Oh, that's a bit scary. And in fact, that doesn't guarantee it, because of course, the length of the confidence interval will vary, because we're estimating the population standard deviation and estimating from our samples. And so that will vary. And here's a distribution. In fact, it's a chi distribution of the MOE values we will get as we use 2 samples of size 50 for our independent group study. If we want to do better, well, let's say we want 99% assurance. We want to be almost certain that we're going to get a confidence interval no longer than plus or minus 0.4 in Cohen's D units. Well, we need 65, and here's the curve there. And of course, we can say, well, 0.4, that's really very wide confidence interval. If you want to go down to 0.3, well, then you're looking at 87 on average, or 108 with assurance, and so on. If we adopt a different design, a paired design, well, then the world changes a fair bit, and we can get away with considerably smaller studies. But we also have to think about the correlation between the, suppose this is a pre-post design, we've got a single sample of size 29. We're assuming a correlation in the population of 0.7 between the pre and the post. And that's not totally unrealistic in some cases. If we go up to 0.8, well, we can get away with a much smaller single sample. And of course, as with power, it's usually used for sort of sensitivity or what-if analysis. And that's what we'd use precision for planning for typically. It would be great to have really good tools. Ken Kelly and others have worked mightily on preparing the, doing the statistical analysis for this. It would be great to have a sort of G-power for precision for planning, and I hope there are folks out there working on them, and there are some resources that help, and Bob's got links to some of those, but there's a big future here for developing precision for planning as a technique for planning our studies. Let's go to dances. This is the core business. So here I've got a normal distribution, and I've filled it with dots just to give the idea that we've got lots and lots of data points there, and I'm going to take a sample. Now let's take a sample of size 20, for example, and let's take one. And there we have it, and there's the mean that's just dropped down. Because I'm in the computer playing games, and this is a simulation, pardon me, I've marked the population mean mu, but I can easily turn that off if you prefer. Take another sample and drop down that first mean, and now let's run them like so. And there are several things we can note there. The pattern of data points in the individual samples really dances around. They tend to be clustered in the middle because that's where we've got a higher heap, and we get ones out at the edges just every now and again. And here we have the dance of the means, and you can play this at parties. You can put on your favorite sort of doof music and adjust the speed here till you get it just right for your choice of music. And of course, if we go to a much different sample size, we get a much narrower dance at the price of taking much bigger samples. Now let's collect them down into the mean heap. Make it nice and fast. There we go. So the dance of the means leading to the mean heap, and we can put the sampling distribution curve on that. That's the theoretically expected normal distribution. We can put standard error lines on that and standard deviation lines up on the population. And so we can talk about standard error as the standard deviation of the sampling distribution of the sample mean. You got that? Make that a chant, make that a song. And what next? Right. The aim all through this, I mean, I guess perhaps obviously, is to try to take basic statistical ideas and make them visual and pictorial and under your hands so that students can use this in the lab, can use it at home, and on their tablet, if all they need is access to the internet, and they can play around with this. To help them start off, if you click the question mark up here, you get a whole lot of tips, and so you get little pop-ups that explain to you various things about what these various controls do. Okay, let's now think about a confidence interval. If we clear all that and go back and turn on a confidence interval, let's turn off the mean heap and take a sample. Aha, we have a confidence interval, a 95% confidence interval. And let's run these down. That's a bit fast, isn't it? Need to enjoy it a bit more on the way. Okay, there we go. And that is the dance of the confidence intervals. Each of these intervals is the same length because I'm assuming sigma is known. But if I shift this to unknown, notice that some get longer, some get shorter. And that's something we can talk about. Now, suppose I want to talk about capture. I turn on capture of mu and I color red all the intervals that do not capture mu. Unfortunately, in real life, confidence intervals don't come colored. Wouldn't it be nice if you could just look at an interval, notice red and say, oh, it missed. But unfortunately, we know that around about 95% of the confidence intervals we'll encounter in our life, in our careers, will capture, and an unknown 5% won't. The interesting thing playing with this, let's speed this up a bit. We can track down here what proportion have captured, and we're on 95 point, 94 point, 95.6, etc. We're tracking round about 95. But if you follow the pattern of where the red comes, it's very hard to convince yourself that it's random. You think, oh, I start this up in the morning and I've got something in the programming wrong because I haven't had any red for quite a while. Oh, suddenly I've got a whole bunch. This is one of the lessons about randomness. It's constantly surprising. In the short term, it's very lumpy. In the long term, it's absolutely 3 decimal places accurate. Leave this running overnight. It's a decent quality random number generator, and we'll get 95.0 for sure here. We can change to confidence intervals of, say, 90% if you prefer. They're shorter and we've got more red ones, or 99%. They're longer and fewer red ones, and play around. We can do it with sigma unknown, and they all change length, and very often they change from being red to green. Oh, there we are. We've got 95% unknown, and we've got a whole bunch of red ones. Well. the count is cleared, and now we're still tracking around about 95%, even though sigma is unknown. So these, not only is it a decent quality random number generator, but these formulas, these strange formulas of T and degrees of freedom, do actually work by giving us confidence intervals that have this property that 95% of the bands do capture. Okay, next, switch on this bottom panel, the dance of the p-values. So I've set this up arbitrarily, so the population has a mean of 60, and I'm going to take my null hypothesis as 50. You can make up some cover story about this, and I'm going to take a sample, and I'm going to turn on the sound. There we go, take a sample. And here I had a sample, and it happens to be way over here. In fact, it even misses mu. Can I do this at the same time? I can too. But here we're mainly looking at how this confidence interval compares with the null hypothesis value, because of course we don't know in real life what mu is. Can I hide mu? Will I still get it? Ah, yes, I can. Okie doke, and I can hide those standard deviation lines. And so if I look at this confidence interval and compare it with our null hypothesis value, it's a long way away. I get 3 noughts. Let's take another one. Can you hear a sound there? Here's another one. So deep sounds, I hope you can hear deep sounds, are for blue. These are the confidence intervals that overlap. We do not have significance. We have a large p-value. We tear our hair out. If we get one that is way over to the right, like there, we get a slightly higher note and we get a smaller p-value. Now, let's see if I can find a good speed around about there, maybe. Oh, a bit fast. And that is the dance of the p-values. And of course, you can play around with larger and smaller sample sizes, with moving the population mean relative to the null hypothesis value. So you get different values of Cohen's delta, the Cohen's d in the population. This one is 0.5. And correspondingly, you will of course get different proportions of these confidence intervals overlapping 0. The dance will be way out to the right, and you have lots of very small p-values, or it'll overlap a lot. You'll have lots of very large p-values. But in every case, the dramatic thing about this is the amount of variation here. Now, as researchers, just think what we know. We know only our own interval, which might be this one. And if I just tell you one confidence interval, does that give you any idea about the dance? Well, yes, it does, because the extent of that interval gives you a fair idea about the amount of bouncing around. Any one interval here gives you some idea of the freneticism of the dance. It doesn't tell you where the dance is, but how wild it is. But if I just give you one of these p-values, do you have the slightest clue as to what dance it comes from? Well, basically no. And that's the crux of the argument. Sure, we can translate backwards and forwards. Let's look at any of these. Here's a confidence interval that just overlaps. And so we know that the p-value is just over 0.05. And there are some simple rules of thumb that allow us to eyeball from a confidence interval position relative to null hypothesis into the p-value, and vice versa. So if I gave you one of these p-values, you could then, provided you know where the mean is, you could then figure out what the how long the confidence interval is, just back at my very first slide. And so that would give you a much better basis for interpreting the result than just the p-value does. Let's move on. Oh, one more thing here. Yes, indeed. Let's close this. One more of Gordon's goodies. I've got the possibility of using different shape distributions to sample from. So let's do a custom one, shall we? So I'm going to just draw something that's a bit weird. Whoops, hang on, let me do that again. So that's a weird and skewed distribution, and I'm going to take samples of only, say, about 5, and I'm going to make it happen quickly, and I'm going to turn on the mean heap and the sampling distribution curve, and I'm going to run that down. And if we let that happen for a little while, we'll find that this theoretical normal distribution for the sampling distribution predicted by the central limit theorem fits amazingly closely with our empirically obtained pile mean heap. And if we have this distribution on the top super skewed, we'll find little bits of misfit in the tails, even with samples as tiny as n. So this doesn't guarantee that the central limit theorem applies in every real case with real data, but it does give us a fair bit of reassurance that when we make the assumption that the sampling distribution of our statistic is normally distributed, well, this will cover a fair range of cases of types of distribution in the world, which is reassuring for parametric statistics. Not the full story, but reassuring. I'd better move on here. Correlation, we can do lots of good things. Let's turn on R, and we generate a new data set, each with a chosen correlation. So these pictures in the textbook of a nice cigar-shaped zeppelin of dots. Well, as usual, random variation, the extent of sampling variability is much greater than we might think. And we can put regression lines on this as well. And finally, dance R, we can sample from a population represented by the pale grey dots. And so we, oh, sorry, I should turn on the value of R up in the top left. And these values move around a lot. Oh, I'm doing it a bit slowly, aren't I? And we can also do a dance of the R values and sample. Let's take a value of, in the population of, 0.89, good as any. And then turn on confidence intervals and the row line and capture and the R heap. And what should we get? What haven't I put through? Dance with the R values, display confidence intervals. They're over on the right, just about hidden from me. Perhaps they're hidden from you too. But we can play around and notice that confidence intervals on Pearson's R are highly asymmetric. Now, I need to move on. How can I screen share a different thing? Perhaps
you should be able to just switch right over, Geoff, I think.
If you stop sharing your screen and then reshare it, when you reshare it, look for the one that's called desktop instead of specifically PowerPoint, and it'll share your entire screen, whichever you have open.
Now, are you still seeing that?
Yep, sorry, we're still on your browser. You'll have to stop and reshare.
This is really quite slow. Now, I hope you can see PowerPoint again. Yes?
Yes, we can.
Okay, good. Okay, I need to move on. Right. A quick question. You carry out a study and calculate P is 0.01. What p-value are you likely to get, an 80% chance after 0.1? An interval this wide or even wider or wider or wider? Lock in your answers. I'm not going to ask you, but you figure it out. This is all published quite some time ago, the formulas for what I'm just about to do. And in fact, that is the distribution of the replication p-value after us. If you see a study that reported p equals 0.05, and then you replicate it precisely, whatever its sample size, whatever its power, whatever its true effect size, this is the distribution you're sampling for. So lots of very low p-values, but still quite a few larger ones. If it's 0.1, of course, you'll on average get smaller p-values, more up here, and even, but still some down there. Let's take the 0.5 curve, split it into 38 equal areas, label each of these areas with a p-value, for example, 0.2 or 0.7 or 0.00 something, and we'll get 38 p-values that represent this curve. So here's the distribution of them. 7 are less than 0.01, 15 of them are greater than 0.1, and if I distribute them haphazardly around a roulette wheel, this is what it looks like. So the dark blue are the p greater than 0.1, and the bright red is less than 0.01. And if I spin this wheel and put in the ball, are you holding your breath? What result are we going to get? 2 stars. Aha, great. You'll get that postdoc position after all. I hope that even in these couple of seconds, you can get a slight bit of this sort of visceral feel of the edge of your seat as to whether you get significance or not. This is the thing we're trying to move on from by illustrating the enormous variability of the p-value. One more time. Okay, on a different occasion, you've found a study at 0.05, you replicate it precisely, and what do you get? Where will the ball stop? .67, but of course the tiniest flip of the wheel, it might have been 0.03, it might have been 3 stars, it might have been 0.39. And so here's the distribution for following 0.01, following 0.05, following 0.01, we get rather more of the 0.01s and rather fewer of the 0.1, as you'd expect, but still the most dramatic thing here is that we've got very wide variability. And in fact, the answer here is the P interval, the interval with an 80% chance you'll land within, 10% less than this, 10% greater than this, is as wide as that. And so P intervals following these initial P values are very wide, and the probability of getting P less than 0.05 following these initial p-values are really worryingly low. Get 0.001, which we've brought up thinking as certainty, you've got a 1 in 6 chance you won't even get 0.05 on a replication. There are a couple of videos here that explain that in a bit more detail rather than the breakneck pace that I've been going through just recently. So when you see a p-value, think of the dance of the p-values, significance roulette, the enormous length of this interval, the picture, and we've got to do better. Confidence intervals, Bayesian estimation. I hope you caught EJ's great talk a few hours ago, bootstrapping quantitative modeling. Now, for the real highlight, courtesy of Bob, and Eski in Jamovi. Now I might need to stop and go to here and share screen. Aha. Right. I actually skipped a couple of slides, but I won't go back to this. Download Jamovi onto your computer, install it really easily, open it up, and this is what it looks like. You've got Data tab, Analyses tab, and over here, I should be able to see, yes, there we go. Jamovi library, let's have a look at that. And in Jamovi, we've got a whole bunch of modules. Bayesian methods, this is a port of the JASP Bayesian analyses, and you could install this in Jamovi. Or Bob's one, Esky, the stuff he's been a big chunk of his life for the last year or two, and for the next little while, developing these wonderful analyses, emphasizing confidence intervals, and I have that installed there. So now I'm going to do one example, which is a two groups example, and I was planning to zip backwards and forwards between back to the shared window is closed. Okay, so if I go to here, share screen, I can go back to PowerPoint and here. Esky and Jamovi, that's where that link takes you. A bit of stuff about downloading Jamovi. This is what the Jamovi homepage looks like. You can even try running it, the online version, although you can't put modules into that yet, and download the current version, the latest version. And here is the little example I'll talk about. And here's the data set that I'm about to use. And we're going to see a picture like this, which we can interpret. Now, if I do that, can you see that Jamovi screen now?
No, we still.
That didn't work either. Okay, sorry. Let's try share screen and go to Jamovi there. Now, can you see Jamovi screen? Can you see the data down here on the left?
Yes, good.
Okay, true. So now I've got, because I've installed it, I've got some extra menus up here. This is the Esky menu, and I've got descriptives, estimate mean, two independent means, paired mean, proportion, difference between proportions, and that is what we do instead of chi-square, correlation between two correlations, meta-analysis, raw scores, Cohen's D, and R. A great power of goodies. And let's take independent mean difference, and I'm going to use this as my dependent variable, and that is my grouping variable. And so I get comparing two means here, and it's working on it, my picture there, and I've got various options. I can make these do various things like this. Now, here we've got the picture as in our, well, both my books actually, both the intro book emphasizing if we've got a difference between two groups here, we've got the mean and confidence intervals and the data for each group, and we've got the confidence interval on the difference between these two on a differences axis, perhaps with its plausibility curve on it, and that's the thing we interpret. We've got a p-value there, and in future versions of this, there will be even more scope to change things about these about this display. You can just right-click and copy and put it into your report. And let's go and do something different with the same data set. Estimate a mean. Now, this is a version that is not available in Jamovi yet, but it's one that Bob's working on for a single mean. And so I'm just going to do a simple estimate of the mean for this whole data set, all the IAT scores. And here I can, I've got lots of options for things I can control and adjust. And so I've got my estimate here and all the data represented. And I could even have detailed output where I've got a whole lot more summary statistics along the way. And at the moment, we're working on optimizing this sort of layout so that for beginners using the book, everything should be under their fingers. And for power users, then they've got lots and lots of scope. I'm going to rapidly move on. I'm running out of time. Let's try meta-analysis. Now, can you see that, still see Jamovi there and meta-analysis?
Unfortunately, it's still the old window.
It's still the old window. Oh dear. I have to close that. And now share screen and go to that. So we've now got a file we're going to use for meta-analysis, and I'm going to meta-analysis of raw scores. Aha, here we go. So here's my meta-analysis of a many labs study on the IAT. And down at the bottom, I've got the diamond result for a random effect and for a fixed effect. And we put that in because we wanted to talk in the book about heterogeneity, the extent to which the variability here is larger than you'd expect in the dance of the confidence intervals. And this is indicated by the extent to which the random effects confidence interval is longer than a fixed effect. We call it the diamond ratio, the ratio of this length to that length, trying to bypass the complicated heterogeneity equations and definitions and interpretations, so that even beginners can get an idea of heterogeneity, a very important idea in meta-analysis. And I've been teaching meta-analysis for approaching 20 years to beginning classes. Do it in terms of a forest plot, dead simple, they just get it. Now, I'm again going to have to do this in a roundabout way. Sorry about this. Share screen and go back to here. These are the things I had planned to talk about: the diamond ratio and interaction another great goodie in Calin-Jageman that gives us a picture like this. And we're looking at the interaction in a 2x2 independent groups design. And that turns out to be the difference of two differences. So it's the difference between social plea and social no plea. Sorry, starting again. It's the difference between functional plea and functional no plea, and difference between this and this, difference of differences, which turns out to be, via these dotted lines, about 9 on this scale there. And, oh, here we are down there. So you can eyeball this at about 1 and this at about 10, and then the difference between the two is about 9, and here it is down there. And we'd argue, and then you've got a confidence interval on that interaction, and that is just short of 0. So the p-values are a bit less than 0.05, but not as low as 0.01. It's probably about 0.02. And that, in fact, accords with the value you get in a standard old style ANOVA there. But we would argue much more informative and much more indicating of the degree of uncertainty with which you're estimating the interaction. Again, estimation wins out. This is a slide slightly adapted from Bob, with a whole lot of resources and links suggesting all sorts of things you could do to take this up and use it with your students, as well, of course, waiting for this this last book. So in conclusion, and hurriedly, teach and use estimation, the new statistics, as part of open science from the very start. Avoid all those terrible things here at dances. And for data analysis and great graphics, Calin-Jageman. So here are the two resources, the main thing I have to tell you about today. And it's, for me, after decades of significance testing, having now several decades of doing it with estimation, it's just been a joy. We don't lose those smart students in first year who just have enough insight to realize that p-values is such a weird back to front thing that they just can't accept it. So they go off and do something else instead, which is very sad. If you go to this link here, this is the publisher's page for the first edition. Click and read. You can see chapter 1 there. That's the full story with pictures but no formulas, and the 15 following chapters are just bells and whistles. Here's the basic thing about open science and estimation. So here are some of those links again. Second edition we're beavering away on, and I'll close with the greeting, the new statistics greeting. May all your confidence intervals be short.